Okay, hey everyone, welcome to this lecture about transformer neural networks. We call them transformers in short in machine learning. Before we dive into this lecture, I would like to quickly give credit to Christian Lessig, on whose slide deck I built up this presentation or this lecture. My name is Matthias. I am a machine learning scientist at ECMWF. And before we dive into transformers, which are a pretty versatile and very prominent machine learning architecture, deep learning architecture nowadays, they are present in almost every machine learning model today. And before we dive into the transformers, I would like to give a quick introduction about my background, where I'm coming from, what I'm doing at ECMWF, and then we will dive into transformers, what they can do, what they are popular at, and what they aren't doing so well. Good. With this, let's jump into it. About some of my background, I'm a cognitive scientist by training. So I started doing my bachelor's and master's at the University of Tübingen, and in particular during the master's, I was pretty much caught by machine learning, by artificial intelligence, and then I specialized in artificial neural networks. I was working a lot with recurrent neural networks, which were state of the art, or basically the model to go if you wanted to process time series data. And later I proceeded with a PhD about global weather prediction with neural networks. And that's also where I got in touch a lot with transformers. But I still was working quite a bit with recurrent neural networks due to the time series of weather dynamics in general. Now, what I'm doing at ECMWF, I joined the weather generator team at ECMWF in July 2025. The weather generator, you see it at the bottom right. It's basically supposed to be a foundation model. It's operating on various input data sources. It receives like simulation data, observation data, all kinds of different streams coming into the model. And then it produces a kind of rich latent state. From this latent state, it is supposed to deliver certain downstream tasks like forecasting, super resolution, like increasing the resolution of some temperature map, for example, or also best state estimates. And fitting to this lecture today, the weather generator consists of many transformer blocks. So I'm working a lot with transformers nowadays. And I'm delegated more within this weather generator project for, I'm sitting in the Earth System Predictability group, and I'm focused on extended range. So I'm trying to make weather generators stable over long periods, like over long rollouts, that we can generate forecasts in sub-seasonal or seasonal scales, even like multi-week, months, and ideally also years. That's my background. Let's look a bit about the topic of this lecture today. What are transformers made for originally, and why are they so popular nowadays? Originally, transformers were designed for sequence-to-sequence modeling. That is, for example, like for processing sequences, basically. And a very popular task is, for example, next word prediction in a sentence. So if we are facing this sentence, for example, my house is, then you may complement this sentence and continue it in some reasonable way, hopefully. And if you have this kind of house in mind, you may come up with my house is tiny, for example, as a next word in the sentence. And transformers originally were designed to do this kind of task, to do like next word in a sentence prediction. And that's also what large language models nowadays are doing. They receive a certain context of words, and then they try to predict the next word that is coming given the context that they are having. In this lecture now, we will have a look at, in particular, what are the ingredients that actually make a transformer a transformer. What are the crucial components that are involved in this architecture? And why is the transformer architecture so prominent nowadays? Why is it part of almost every machine learning model today? Because literally, transformers are a building block in almost any deep learning model that exists today. For example, GPT in ChatGPT, it actually stands for Generative Pre-trained Transformer. So any large language model that we have today is based on transformers, or you have transformer building blocks in any large language model today. So they are super prominent. Coming a bit about to the motivation why transformers have been developed. Traditionally, sequence processing tasks like time series processing, that was typically realized with recurrent neural network, which I also mentioned very early when I introduced myself. Recurrent neural networks were the standard for sequence-to-sequence tasks up to 2018-ish, when transformers were invented. And transformers technically were designed for time series processing as well. Like, for example, this task of complementing a sentence or predicting the next word in a sentence. And looking a bit more about why transformers have been invented, I would like to motivate a bit more what the reason is, like what the drawback of recurrent neural networks was actually. Because recurrent neural networks, they were working pretty well. They did this next token prediction or next word prediction fairly accurately. But they had some, like the recurrent neural networks had one really major drawback, and that's something we are looking at here. The recurrent neural network, what you see here in blue, like this blue box kind of represents the recurrent neural network. It receives an input x in time step t, and this input that is kind of accumulated in this recurrent neural network. So the recurrent neural network, it sequentially walks over its input, like over the input's time series, and iteratively aggregates the information that it sees when walking over the time series. So if this is a sentence, for example, my house is, then the recurrent neural network would first see my, then it would proceed to the next word, house, and then to the next word is. So it has this sequential processing operator of processing its input. And I mean, one powerful aspect of recurrent neural networks is that they aggregate all the information that they are seeing on the fly into a so-called hidden state, like this H. H is basically, if you look a bit more carefully on it, it's a combination of the input X, which is weighted by some input weight matrix, like input to hidden weight matrix. So the input X in time step t is processed and then comes into the neural network. And simultaneously, we have some hidden state that has been, like, that exists from previous time steps. And this hidden state is also combined with the current input. So basically, what the new hidden state of the neural network, like ht+1, like the hidden state in the next time step, what it will consist of is basically the entire history of ht so far, plus the information of xt coming from the current time step. So an RNN is basically aggregating any information over the past into a latent hidden state, h, such that from the latent hidden state, which encompasses all the information, it can generate a meaningful prediction for kind of, for example, predicting the next sentence, the next word in a sentence. So this has two properties, basically. A recurrent neural network has some kind of an implicit connection to past states. Like in theory, a recurrent neural network can remember everything that it has aggregated over the past. Like if you start the recurrent neural network and walk over a sequence, it has in principle the capacity to remember each individual bit that it has been confronted with. This connection, however, is very implicit. It's somewhere in the hidden state, and it's pretty opaque and hard to understand what kind of information is represented in this hidden state. Now, a different and kind of major drawback of recurrent neural networks is that they are very difficult to parallelize. Like, due to the sequential order of processing the time series, they always have to iteratively walk over a sequence. They literally have to wait until the last word in the sentence can be processed. They first have to process all the previous sentence words individually before they eventually can process the last word and then create a prediction. And this is a kind of a sequential problem that can't be parallelized for recurrent neural networks. And that's exactly where transformers come into play, because a transformer is, in principle, it's an architecture that can be parallelized much more efficiently, and apart from this, it has a very direct interaction between the information of the individual words in your sentence, and that's something we will look at in the next. So attention is all you need. That's a paper from 2018 from Vaswani and colleagues, where they basically introduced the transformer, and from that point on, the transformer basically overtook RNNs and was kind of considered as state of the art for time series processing. But now, what is actually making transformers, or why are transformers that powerful as they are and so universal? The most important part of transformers is the so-called attention mechanism. The attention mechanism, you can consider it as something like literally attention. Like if you attend to a certain scene or to a certain sentence, you may attend to certain words more strongly than to others. And this is some process that is implemented in this kind of attention mechanism in the transformer paper. So we come up, first of all, the model is confronted with kind of a time series, in this case, a series of words. It's basically my house is, blah, blah, blah. And the first step, how we proceed is we encode all the individual words into so-called tokens. TI, like for each single word, we encode this word into some latent space, some hidden or latent state, which is an e-dimensional vector. Each word is converted into a so-called token, like TI is a token for the word I in the sentence. Now, what happens next after we have encoded all these words is we want to propagate information, or we want to make these words interact such that the model has some way of learning how, like, what content does the sentence have, how do I have to process it in order such that I eventually can make a prediction. And in order to make a reasonable prediction of the next word in that sentence, I first have to understand the entire sentence, what basically the sentence says so far. And for this, each of these tokens is compared to every other token in the sentence. And this is basically just done by applying a dot product. Like here we have two tokens visualized in this three-dimensional space, and these tokens, they are basically vectors showing in certain directions, and we can compare how similar are two tokens by just comparing or multiplying them, like computing their dot product. So we basically compute the similarity of all the tokens which represent the words from the sentence. We compute the similarity of each of the individual tokens, and then depending on how similar different tokens are, we will update the token in the next layer. So here on the left-hand side, we have the inputs. My house is tiny and cozy, for example. This is basically, let's start with my, let's say TI in the first iteration, or in this TI, well, say I is 0 at the moment, and we consider my. We now want to create a kind of an update token of TI, which consists not only information from my, but from all the other words in that sentence simultaneously. So, and important is, the closer the respective other word in that sentence is, the more information I want to aggregate into the update of my, such that such that my not only consists of my, but also the information of other words that are relevant for my, so to say. So this ti tilde will become kind of, we compute the similarity of all the other tokens, like j are basically all the other tokens in the sentence. And the more similar two tokens are, the closer they are in the vector space, and the bigger their dot product is. So it's approaching basically it's getting a larger value. And then I'm also considering the respective tj more. Like say my and tiny would be very close in that vector space, then the dot product of those two is very big, and ti will not only contain information of my, but also we will multiply tj, which then would be tiny, with a large factor, and then kind of the tilde I will contain much of my and much of tiny. So in the next layer, we will have this tilde, like t tilde I, containing lots of information from different tokens. And this is the principle of this attention mechanism. We still want to make sure that the activities in the neural network, that they don't exceed certain thresholds, and we want to kind of normalize our activities on the fly. And that's why the Attention is All You Need paper introduced this softmax activation function. The softmax, basically, it has two properties. It's basically it ensures that the distribution of the new activity is not exceeding. It's basically some kind of a normalization. And at the same time, it is some kind of a nonlinearity, which is good to have in general, because we have a nonlinear projection then, and that makes our model more powerful at learning nonlinear dynamics. So here, for example, we have what actually, like on the left-hand side, we have some distribution for different values, and we see like the according intensities that are like, consider the x-axis as the different words in the sentence, and then the y-axis as the dot product with the word that we are comparing at the moment. And we see that like the third word in the same sentence has a very high dot product, so this would aggregate as a big proportion into the updated token then later on. But we also see on the y-axis that the value exceeds like 1, or it's very big. So we would take lots of the new word into the updated token, and this might actually lead to our token growing bigger and bigger, and like kind of exceeding activations that we want, like that we want to prevent the model to go into. Like normally we want like a model to be kind of in a standard normal distribution. And if we don't control for this, our values might just grow bigger and bigger, and then our gradients and signals just become kind of screwed up. So the softmax, basically, it normalizes this, and we see that the sum of all these dot product eventually this yields 1. So we make sure that the accumulation of all the information basically does not exceed certain values. That's what the softmax does. And now the question is, well, we have this attention mechanism, like we compute similarities, and we update our token to contain information from other tokens. How can we now make this learnable? How can we make sure that this can be approximated by a neural network? So far, this is just theory, what we would like to have, but there's no neural network involved so far. So what we come up with, or what the people in the Attention is All You Need paper came up with, is they design 3 matrices, PQ, PK, and PV. And these matrices, they basically create, they are all multiplied with the tokens, and then they create query, key, and value pairs, or basically vectors. So instead of just having the tokens, we actually multiply the tokens with 3 weight matrices and then gain 3 times the number of tokens. And the first set of tokens is the queries, the second is the keys, and the third is the values. And that's what we put into this equation. So we have queries, which we multiply with keys, and those, like the result of those, is normalized by the softmax, and that's what we eventually multiply with the values. And this is basically our learnable attention mechanism. And kind of visually illustrated here, we see basically our tokens, Ti. Then we multiply this kind of each token with the PQ, PK, and PV matrices. So we have 3 times the tokens, where the first set of tokens is the queries, the second is the keys, and the third is the values. So technically, what I usually understand an attention mechanism as is it implements some kind of a learnable lookup table, if you want so. Like Q, for example, like say QI is a certain word in the sentence, and I'm comparing QI with all the other kind of keys that are kind of the coming from the other multiplication of the or transformation of the tokens. I'm comparing all the my current word with all other keys, and the larger the dot product is, like the more similar query and key are, the more I take of the respective value standing behind the key. So I'm having a query. I say, well, I have word my, and I'm looking for how similar are all the other words. And the more similar other words are, the more of this respective word I'm taking. So this is basically our learnable attention module, and it's getting a bit more complicated because we don't have this learnable attention module only once, but we have it like h times. We have like multiple heads, and each of these heads implements its own learnable attention mechanism. And what this leads to is basically the different heads can start to learn different attention mechanisms. So for example, the first head, it might start to learn kind of looking at these kinds of relationships, like attending to this kind of pattern. This might be the first kind of relation that, or this might be the relation that the first head learns. But there's another head which might learn very, very different relationships, like for example, much longer ranged relationships than the first head does. Like the first head seems to, in this example, seems to look at very close neighbors, nearby neighbors, whereas the second head, it has like a much longer range dependency. And that's also where you see, compared to RNNs, we have this very explicit. We see that the second head, it has these very long kind of the intensity or the saturation of these colors basically represent the similarity of these words. And then we can also see, okay, if our model looks now or basically inspects law, how much would it attend to all the other tokens, like all the other words in the sentence when it's looking at law, like when it is at the stage of updating the token of law. And with this kind of multi-head procedure, we have kind of a versatile and pretty powerful kind of a mechanism that can be applied pretty versatile, as I mentioned. And here we have this kind of prepared somewhat visually again, some in a schematic. Like we have our input. Our input sentence, this is converted into some token sequence. And then these tokens, they are in parallel processed by n heads. And each of these heads comes up with some kind of some proposition of tilde heads. Like each of these heads creates its own kind of suggestion how the respective head would update the tokens. And typically what you do is, in the end, you aggregate the suggestions of all these different heads and take them all together, typically by another multi-layer perceptron or something that then just aggregates this information into one kind of major update. So this is going to be the output of this layer, and then we can add another layer to transform it even further. What is kind of added typically to this architecture is still a layer norm, because as I mentioned earlier, we typically want the activities of our model not exceed certain values. So we often have like these layer norms to stabilize our activities in the network, and having a layer norm before the tokens go into the heads seem to be very promising. And then we have a skip connection basically to make the model rather learn deltas instead of predicting everything like in absolute values again. And this is already it. This makes our attention block. And this attention block can now be combined with yet another component that is crucial to the transformer. We have this multi-layer perceptron, which operates on kind of a different axis. Intuitively speaking, what this attention block does, it mixes the information between the tokens, and then the multi-layer perception block, it's mixing, or it's kind of cleaning up the information that is within one of these tokens. Like a token, as I mentioned, is a e-dimensional vector, and the MLP now kind of rearranges or kind of does some operation on each individual token, but it doesn't like consider the other tokens when refining each individual token. So we have these two parts, and that these two parts they can kind of make our transformer block. And as I mentioned, like what the attention block does, it's basically it's computing all the similarities between the different tokens, and then we have this multi-layer perceptron block, which basically realizes some kind of transformation from vector space A to vector space B. So we have all these similarity measures. We have kind of updated tokens like these tilde, T tilde tokens, and then these will be projected into a different space by this multi-layer perceptron, and then we again do some kind of attention block, which does another kind of similarity computation in this new vector space. And this basically, if we repeat this multiple times, we have this kind of mixing and transforming behavior iteratively, and this is pretty powerful because you can realize kind of any kind of function that you want with first computing the similarity of tokens, then converting it into different vector space, and then again doing some similarity. So there's kind of an open stage of what you want to achieve. This architecture is very versatile, as I mentioned, due to this pretty uniform universal principle. Now looking at one crucial ingredient that is still missing until we have the transformer complete is a so-called positional embedding. Without this positional embedding, the transformer would in principle be blind to the order of the input sequence. Like it wouldn't have any idea, any notion of which word comes in at which position. Like does my come before house, and what is basically the order of the input words. And this is kind of dramatic. If you wouldn't know anything about the order of your inputs, then how would you create a reasonable prediction of the next word? And the problem is like why the transformer has no notion is that it is all these inputs like my, house, they are all kind of fed in parallel. Like these are all provided to the model in parallel, and then it just does the simulation, the similarity measure, but it has no notion about which vector comes first, which comes second, etc. This is all being computed in parallel. And the trick that people come up with is basically adding some kind of a positional encoding, and that's basically just a kind of harmonic positional encoding that tells like a combination of sine and cosine, which tells the model at which position in the sentence each word is. And once you add this positional encoding, your transformer has a notion of kind of order of the input tokens. So a crucial question now is, given we have this transformer, it has been super powerful and proven very effectively on sequence-to-sequence processing, like in particular text translation or such. But can we also apply it to other tasks, like vision tasks, for example? Can it also operate on pixel, like on images that consist of hundreds or thousands of pixels instead of just a one-dimensional sequence? Like, so far we have only looked at how the transformer would process kind of a sequence of words. But what happens if you want to process an image, like, for example, this picture? How would you process such an input with your transformer? And this is kind of a new paper that has been proposed in 2021, where you basically think about how, like, how do you define the token of your input? So what they actually do is they separate the input image into n by n patches. And the reason for which they do it is by separating the input image into patches is they can say each of these individual patches now represents one token. Like formerly in this word or in the sentence context, we had each single word represents one token. And now with images, they say, wait, well, each individual patch in our image represents one token. And so they again come up with kind of a huge number of tokens, which they can feed through their transformer. So what this now changes to is basically everything changes the same. It's only the encoder that changes. Instead of receiving certain words, the encoder receives small patches from the image and converts those into the tokens. Like the tokens are, again, they are just some e-dimensional vectors. And then each of these tokens, each of these patches is represented as some token in the latent space of the model. And then you can directly apply your transformer and do all the attention mechanism and all the attention magic. You don't have to touch the architecture in any way. So this is pretty convenient, actually. You just have to think about what is the smallest but non-trivial bit that I have to convert into the latent space, such that I have the tokens on which the model now can operate. Right. And now applying this to atmospheric science, we have this paper from Lessig and colleagues. We have seen who are basically processing atmospheric science, atmospheric states with a transformer. And when looking at the individual attention maps, like at the different heads of the transformer, I have to drink a bit. Looking at the individual heads and what they attend to, we see that each of these different heads expresses its own attention map. Like this one here, for example, in the top, it seems to kind of capture the broad situation and capture like a wide information from the entire input, whereas others seem to rather focus on kind of the sting of like the swath of this tropical cyclone, the tail. So each, like, we have these different heads, and they, depending on the task, they start to evaluate or kind of develop their own attention mechanism that seems to be valuable to solve the task. Now, originally, what transformers were designed for is basically, and that's another pretty powerful mechanism of transformers. They can't only operate on a single kind of quantity or entity, for example. You can also kind of cross different entities with each other. Like for example, you can do a language translation very seamlessly. Like for example, you encode language A, and then you take the decoder to decode from the latent representation to decode an arbitrary language B. And the way this is done is basically you have your transformer, you have your embedding, and then you have your encoder, which comes up with some kind of latent tokens. And if you want to transform now these latent tokens, you can take the queries from the latent from the input language basically, and then combine them with key and value from another language. Like this would yield pretty universal latent states here, for example. Like this latent state would be language agnostic. It would just contain any information from any language. Like you have, for example, you have German, it might be mein Haus, and then you have kind of a latent representation that stands for mein, and you have a latent representation that stands for Haus. But that would be language agnostic, because now what you can do is you take that latent representation for mein and try to find similarities in English, and then ideally what should come up is my. Like you would find the link between mein and my by just taking the queries from the encoded latent, and then trying to find the similarities of a target language. And this works very well for transformers. And here we have an example where you see basically this is an attention map where we see, for example, like how different words attend to each other and how well this matching actually works. Like if the model is confronted or if the model processes book, then it kind of translates this to livro, which is pretty much what we want. So there's now a couple of extensions still. Transformers, they are super powerful, but they have their limitations in terms of a quadratic complexity. And this is pretty problematic because our model, the longer the sequence becomes, the more tokens we have, the more pairwise comparisons we have to compute. Because in order to do the cosine similarity thing, like the dot product, we have to compare every token with every other token. And the longer our sequence becomes, like the more complex our problem becomes. And this grows quadratically. So this is really kind of computational-wise getting very expensive quickly. So there's some kind of approaches like sparse attention, where you only compute the attention between nearby tokens, for example. Like for example, if you process a sentence, then you wouldn't want to or if you say you process an entire document, then you may not want to attend the very first word in the document with the very last word in the document, but you rather kind of slide through have a slicing window through the document where you only compute the attention over this kind of respective window. And this kind of narrows down your complexity substantially. And then there's a couple of other extensions like shared key and value between the different heads, such that not every head has to learn their own key and value, or also like other normalization techniques like query key layer norm, such that this seems to be important for larger models that your activations stay in a handleable, manageable regime. Now, why should we use transformers? The biggest pro of transformers is basically its flexibility, and that's pretty impressive actually. Like the transformer is somewhat agnostic to the structure of the problem at hand. Like you've seen, you can throw one and exact the same architecture if you want to text translation, if you want to process sequences of a text. And you don't have to change anything of the model, of the core model, when you go to vision tasks. Like you can directly, you only have to change the way you embed your tokens or your input into tokens. And then once you are on the token dimension, you can just throw your transformer on it, and that's super agnostic kind of in terms of structure. Then missing values can be handled very naturally. Like for example, here in this, this was kind of a masked autoencoder paper, which is pretty impressive, I think, where you have kind of an input and you mask large proportions of the input and you only provide those tokens that are meaningful to the encoder. And then you ask the model to kind of paint in the missing bits. And this is also straightforward working with transformers. You only provide it with those tokens that are meaningful, and then you ask it to fill up the kind of all the tokens that were missing. I wouldn't want to think about a way how you would implement a convolutional neural network to do this kind of inpainting. This would be pretty painful, I would say. And then another like huge aspect for transformers is really their parallelization, because they take the entire input series and process everything in parallel and then generate the next token prediction. They don't have to, like the RNN would have done, they don't have to walk over the sequence iteratively, like step by step. No, they really just receive all the inputs in parallel, compute all the similarities, and then directly come up with kind of a complex latent state from which they then can produce an estimate of the next token of the, like a next word in a sentence, for example. The caveats, the drawbacks of transformers is their cost. Like literally, we have this kind of high memory footprint where the longer the sequence becomes, the more quicker you kind of run out of memory because of that quadratic complexity of token comparison. And also what can be kind of a drawback is that you have very little inductive biases. Like this transformer doesn't assume kind of neighborhood in your data. It doesn't have like so many inductive biases like a convolutional neural network, for example, has. And this also means that the functional space that a transformer can approximate is just huge. It can easily approximate any kind of function, but that also means it needs lots of data to learn actually to really approximate the function that you wanted to approximate, and kind of such that it discards all the other options that it could actually approximate, but it shouldn't in this task that you are interested in. Now at the end, I still like to bring this quote, which basically tells it somewhat diminishes the role of the architecture nowadays in deep learning. And there was this paper where they said, our work reinforces the bitter lesson: the most important factors determining the performance of a sensibly designed model are the compute and data available for training. So what this says is the architecture that we have doesn't matter so much. It's basically the driving factors are how much compute do we have and how much data have we available to jump through our model. And that's actually where transformers scale, because they are extremely optimized. They are due to their parallelization nature. You can really push like huge loads of data through this architecture, and it's really a scalable architecture where you can feed very much information through that model just to learn a reasonable function. And that's just the advantage also over recurrent neural networks. Like a recurrent neural network in principle could do the same, but it would take just much longer because you can't parallelize it that well. And since you can parallelize transformers so well, you can just get more data through this architecture in a shorter period of time. Now, wrapping up, I'd like to say that transformers are pretty much a standard neural network in many applications nowadays. They were designed for sequence-to-sequence and originally operating on kind of processing sentences, but depending on how you define your tokens, they can basically operate on any kind of data. So they can also easily process images, as we've seen with these patches. Now, as I said, the architecture is super versatile, since the only definition of a token is like you only have to find a way how you define your token, and you can apply your network then. your architecture, your transformer. And important to keep in mind is that the transformer is computationally highly efficient, since lots of software is really optimized for transformers, but they suffer from this quadratic memory expenses. So one really wants to apply sparse attention mechanisms in general to make those transformers work. That's it for the transformer architecture. I hope you could take some notes of that. We have some more material in the course. Happy to explore this. And now I wish you kind of all the best with playing around with the transformer and seeing how powerful it is yourself. Thank you for watching.